So thank you all for coming this afternoon. I should say, if I'm doing this for the students here. If you've got questions, I wish you'd speak up. Otherwise, I'll charge forward here. But what I want to talk about is what I see is the third revolution in computing. And as I get ready to talk about this, I thought I would just give you a short story of what happened to me here at Michigan 50 years ago when the computer revolution was just really getting started. And I was very lucky to have ended up at the University of Michigan. I mean, I grew up in Detroit, and this was the good engineering school that you could afford to go to in Detroit if you didn't have a large scholarship to go somewhere else. I didn't realize at the time what a great engineering school it was. So when I came here, as Ming-Eng just said, I knew I wanted to go into engineering, but I didn't really know what kind, mechanical, electrical, whatever. But the first semester of my sophomore year, I took a programming course. The course was taught in the MAD programming language, the Michigan Algorithm Decoder. You put the statements on punch cards, you turn the deck in at the computer center. An IBM 7090 would run in. A couple hours later, you get your printout. That really seems archaic by today's standards, but I mean, I could see then that there was a real future in this. And I think as you look at opportunities today, look for those areas that are not so well plowed, that have, I think, great potential future going forward. So once I'd taken that course, I got a job in Keke Irani's lab in the summer, programming sort of Markov chain models. And while doing that, I learned that Michigan was getting one of the first IBM 36067. It was the first early, I think, I have to turn this off maybe. This is not. I do have a phone nearby. Okay, thank you. Let's see if that works. I'll leave it right here and see what happens. So when I realized that, I got a job in the comm center, modifying a PDP-8, which is going to be the communications concentrator to this time sharing system. And once I got involved with that, then at that point I realized that's where my career was going to be. And so while it was important, the courses in electrical engineering, that programming course that got me initially interested in it, it was also the development work, the research that I got involved with as an undergraduate here at Michigan that really sort of set the direction for where I would go. And actually, some of that work is what got me into graduate school and got me involved in some interesting computer systems with the government and elsewhere. So what I was going to do here was try and describe what was going on during that initial revolution, what happened in the second revolution, and what this third revolution looks like, and what are, I think, the wide set of opportunities available to students that are right at the beginning of this third revolution. So let me see if I can just walk through this and see if it makes sense to you. So the first, the computer revolution, as you look at it, really in the mid to late 1940s, John von Neumann laid out the principles of a stored program computer, as did Alan Turing in the UK, as did Konrad Zuse in Germany. And over time, in the 50s and then 60s, what were called mainframe machines, I worked on things called mini computers, which are lower performance. And they've continued to be used, although they're called servers now and so forth going forward. But there's a fairly large gap from when von Neumann and Zuse and others talked about stored program computing, and they begin to become available commercially. And what really triggered it were a couple of primary technological innovations. One of them is this transistor, obviously, but another one is core memory. Those were critical elements. And let me keep going. And I put in red the things that were going on in Michigan at the time. The IBM 7090, which was, I think, IBM's first really successful transistorized computer. And then, as I mentioned, the 36067, which was one of the first commercially available time-sharing machines. So then, if I keep going, the second revolution was really the personal computer, where you went from one expensive mainframe that's shared by a lot of people to something that individuals can have. And there's a famous computer scientist, Alan Kay, who back in I think 1970 talked about a Dynabook and he's got a famous cartoon where the person's sitting under a tree holding their Dynabook doing their computing. So, Alan had the vision, but again, it was a couple of critical pieces of technology, if I get this going forward here, right? What's going on here? Oh, yeah, a couple critical pieces of technology that were required to do that. One was finally being able to get a full processor available on a single chip, and moving from core memories to DRAMs. And with those two, there was a lot of experimental PCs. I mean, Popular Mechanics had one that called the Altair that people rose. But ultimately, Steve Jobs, Wozniak, formed the Apple computer, and it began to take off. And it really took off in 1981 when IBM came out with the IBM PC, and it went forward. And that's continued to go forward. I sort of think of that in sort of a couple of phases, because the personal computer sort of became the laptop, became the cell phone, and it's now to the point where I've got a line I think you can see here. It's almost penetrated to the population of the accessible people in the world of a couple of billion people. So the next revolution is this third wave on pervasive sensing and the massive amount of data that's collected. People call it the IoT. I think academics call it the cyber-physical systems. There's a lot of different names for it. But this wave that I'll talk about, I mean, it's being enabled by the fact that you're getting entire electronic systems, SoCs, on a single chip. And you're able to do this at sufficiently low power that you can afford to do this. Because one thing I always think of as I look at these IoTs is today, I think somewhere between 3 to 4% of the electrical power in the United States is spent running our electronic systems, servers and laptops. If you're really going to have several orders of magnitude increase in the number of embedded devices in the world, you cannot have 2 or 3 orders of magnitude more energy being consumed to do that. You're going to have ways to have ultra low power. I know some of the work here at Michigan has been focused on that as well as other places, so that's critical. Now, as I quickly walk through that and sort of laid out what I think of as these 3 waves of computing, I've talked about the computing or electronic technology that's required, but on all 3 of these waves, including this current one, there's more than a decade of lag between when the fundamental electronic technology is available, and they took off. And so part of my study was trying to understand what was going on. And one thing I realized is, as important as this computing technology, this integration going forward, is the communication technology that are along with it. So if you just run through these 3 again, the other thing that happened that was critical in the first wave, and it happened probably earliest here at Michigan, was getting the communication network in place that allowed many people to access these time-shared facilities. So this Michigan terminal system, which unfortunately became operational after I graduated and left, tied a network of all the terminals across the campus and research labs in Michigan to the MTS system. And so that was critical. And then as you looked at the second wave, that started out trying to say, how can we just continue that circuit switched communication systems that we use with MTS or the time sharing systems going forward. And the realization was, no, you needed packet switch networks. And that got started with the ARPA network back in 1969, 1970. It grew to ultimately the Merit network, which was here in the Michigan area, I think centered here at the University of Michigan, but included Michigan State and Wayne State, other universities in Michigan. Ultimately, the DARPA network, the Merit network, the NSF network got pulled together into the internet, and that took off. And the other communication mechanism I think that was quite important, in addition to the internet for the global network, was local area networks, so that campuses can get high enough bandwidth to actually make effective use of a lot of these computers. And Ethernet is the one that took off. I put it in red not because it happened here at Michigan, but probably maybe the most important work I did at DEC, although I went there to design VAX computer systems, was getting Ethernet accepted as a open standard across DEC, IBM, Intel, and ultimately PCs going forward. So that was critical. And then if I look at this third wave, many of these embedded sensors are not going to be able to be wired into the rest of the world. They're going to need to be wireless sensors. And as I said earlier, they only work if they're ultra low power. If you look at a lot of these embedded nodes around cities, around factories, much of the power is consumed by the RF transmission and receiving of those signals. And so wireless is going to be essential. It's going to have to be done at very low power. There's ways you're going to have to change the networking protocols as well as the electrical network as well. So when I got done with that, I felt pretty good because I said, okay, I should be thinking about the world not as a computer revolution, but the computer and communication revolution going forward. But you know, my final run on this was that this technology was actually, even the communication technology, was there for a while, and what was behind or what was needed in order for these things to actually explode and become so important. And so that's, so my final rip through these, you got, well, I was a page behind here, so it's wireless networks, is on all of these phases, there's a killer application that actually makes this technology useful to the world. And on the mainframes, it was the development of these programming languages. The popular ones were COBOL for business and Fortran for scientific computing. And again, you know, MAD was developed concurrently with Fortran, largely for the computer science community, and over time became the precursor to ALGOL and a lot of the other computer languages that are available today. But it's those programming languages that enabled financial people, scientists, not to program at the assembly language, but to actually make use of these mainframe machines. And it, you know, and Fortran and COBOL came out in 55, 57, when you sort of moved from a few mainframes to many. You know, there's this apocryphal story that you know, IBM, which initially wasn't in computers, they were in accounting machines, and the government told IBM that, hey, we needed more computers, particularly for defense needs. And they did a market survey, and they thought that 6 IBM 701s or 704s would take care of all the accounting or business needs of the country. And you know, how could it make economic sense to develop these computers if they're only going to sell 6? And obviously, it took off in a great way. So then, if you look at the PCs, you know, in the 70s, and I was at grad school then, and initially at Carnegie Mellon, and amongst the technologists, there was a lot of interest in being able to take these one-chip microprocessors and make these personal computers, but they were really sort of hobby machines at that point. And there's no doubt, if you look at the history of PCs, what got them to explode in popularity and importance was this VisiCalc, the spreadsheet calculator that they developed on the Apple II. And you know, the story is pretty compelling that when IBM would go into their businesses to sell their next generation of mainframes, and they'd walk through the financial offices in those companies, they would see Apple IIs on increasing numbers of desks of the accountants. And when they looked at what those Apple IIs were doing, they were running VisiCalc. And that caused a crash program at IBM to develop the IBM PC that came out in August of '81 and then just took off. And then obviously, you know, a whole set of applications beyond VisiCalc helped continue to drive that forward. The one I got involved with was as PCs went forward and the internet became the way to communicate, people began using it to transfer programs around. And actually, a lot of my PhD work, I was using programs both at MIT and elsewhere back on the West Coast to do my work. But again, it was largely limited to the academic and scientific community. until the University of Illinois came out with the Mosaic web browser, which made it easily accessible to many other folks. And then what I got involved with at DEC at that time was the AltaVista search engine, which sort of a cautionary tale for DEC as we developed that in the research labs. I won't go through all the history of it, but by the 1995, inside the research labs, we said, with this search engine, we can find out anything in the world. You can ask it any question, and you get a reasonable answer. And I went to our CEO at the time, Ken Olson, and I said, look, this is really pretty phenomenal development. We need to take this out to the world. And DEC, unfortunately, could not understand how you would make money with something that just was providing information to people. So it was discouraging, but I went back a second time and said, well, you know, actually, we don't need any of your manufacturing. We just need to take down the firewall between our research labs and the outside world and let the outside world know that this thing's there. So we did that in December of 95, and I always remember, like in March of 96, a marketing guy came back with a book that was like 2 inches high, and he says, there's been more column inches of press written about AltaVista than any product DEC had ever announced or ever produced. And at that point, you know, people realized it was important. We actually were talking to some folks at Stanford, Page, and Sergi, which were getting ready to start off their own company in Google. And some marketing guys scrambled at DEC to figure out, well, how can we make a business out of this? And ultimately, DEC was in bigger problems because they had not made the switch from mini computers to PCs. And so life was getting tough in the 1990s. And so actually in 1998, DEC got acquired by Compaq. And the two numbers I remember about that acquisition is DEC got acquired by Compaq for $9.8 billion. And within 12 months, Compaq sold AltaVista to CMGI for $2.4 billion. And so the money DEC was spending on its research labs, which was less than it was spending on aviation services to fly their executives around in private jets, turned out to be more than 25% of the market value of the company when it was all over. Ultimately, CMGI didn't figure out how to make money out of it either, and you know, Google simply took off. But it is those applications that drove this. I mean, the technology was required, and that was some fundamental work that had to be done in electrical engineering, computer engineering, computer architecture. But understanding how it gets applied and what will be some of the driving applications to take it forward. And I mean, so that brings us to where we are now with this third wave. And you know, I think on this third wave of the information and computing revolution, this third wave, we're in the stage where the technology is pretty much there. But I would say, you know, the VisiCalc or the Fortran or COBOL of this revolution has not really been identified yet. And that's, I think, the golden opportunity out there. It's going to happen. Maybe do it this or maybe it's on the next chart. But the marketing people, when I did this, they didn't like it much. But I tried to make this a semi-quantitative chart. And so you can see on the x-axis is log chart. And each of these waves, in terms of the number of units out there, is about a factor of three orders of magnitude larger than the other. So if you look at what's happened to mainframes, which are now servers in the cloud, I mean, it's gone to several million of these servers out there. And if you look at the PCs and really iPhones, smartphones, it's several billion instead of several million. And you know, all the expectations are is this IoT, if it ultimately plays out, which technology will allow it to play out, and you have connected cities, connected factories, connected vehicles, homes, you're going to go to trillions of these nodes. And so the opportunity there is phenomenal. What's going to drive that? Well, there are a couple things that are happening. I've mentioned some of them on the charts here. I mean, the internet's allowed us to collect massive amounts of data. We've been able to then begin to develop AI algorithms. One of the I think the most promising platforms right now is Google's TensorFlow which they're giving various courses on as to how to analyze this massive amount of data, to train on various images and large data sets, and then use them to build inference engines to be able to drive this network of sensors and actuators. But I haven't got the picture of Fortran or VisiCalc or AltaVista to be able to put on this page yet, which means that for students in ECE today, you're at this juncture where as this next wave goes forward, there's 20 or 30 years of enormous opportunity for engineering innovation and enormous opportunity for startups and entrepreneurial work, just like there was with PC, which was a phenomenal experience, and actually as was the mainframe area. So that's sort of what I think of as the three waves that have gone forward. And now let me talk a little bit about what I think are some of the technical as well as application challenges on this third wave, which is really just getting started while you all are here at school and getting ready to graduate and move into this third wave. So let me go next. About 8 years ago, I had the good fortune to lead a group at the National Academy of Sciences that was to look at what does computer performance look like going forward when people were worried about how well Moore's law was going to continue to go forward. So this is the most famous chart from that report, and I mean, if you can see it, it's all these dots are individual processors, microprocessors, and I don't know if I can walk over this. So I mean, the critical one is you look at the power that's going on here. The relative performance, and it goes up to about 2004. That's when PCs were continuing to get faster and faster. They got up to be about 1 or 2 gigahertz, and it flattened out. Now Moore's law still continued, and the number of transistors per chip has continued to grow. But the thing that really sort of topped it was the power per chip was slowly growing, and once it got to 100 watts or a little more than 100 watts, you could no longer cool that chip without melting the important circuits unless you went to water cooling or some other exotic, expensive device. So that's what's caused the break in the chips, and then the uptick is people say, okay, well, since we can't make them any faster, we'll just put more of those processors on a chip, and so you can get these multi-cores going forward. So what was going on? What was happening in 2004? And people, the popular press talks a lot about Moore's law, but what actually happened in 2004 was this Dennard scaling, which described the technical underpinnings of Moore's law. Dennard scaling stopped about that time. And I won't go through the details of all this here, but the Dennard scaling was you just scaled the voltage oxide thickness wire by alpha. Each generation, alpha is generally a 0.7 or roughly square root of 2. So you get, how did I get this here? You get see if I can get there. Let me get back. You get twice the density, 70% higher speed, less 1 over alpha squared power per circuit, but about constant power per chip. But the voltage you had to scale down by alpha, and once you got down to below a volt in your chip, and the threshold voltage on the CMOS transistors was about 0.3, 0.4. You need to stack 3 or 4 of those transistors to make a circuit work. You couldn't push it any lower and still get them to work well. Although people are looking at sub-threshold circuits now, and that caused this thing to roll over. So, in sort of my summary picture of it was, this is where this is the problem the country or the world faced, which was you look at the performance per chip going up. At about 2004, it broke. It went over relatively flat. And the red line is what people's expectations are for the performance. I mean, people will say, gee, you know, the power available in the cloud is going to double every couple of years, and when AI comes in, you'll be running these more sophisticated AI applications, and you know, it'll all be run in the cloud. Well, if right now the power of our computing infrastructure is taking 3 or 4% of the energy of the country, you can't have that energy go up by a factor of even 10. I mean, you couldn't have half the power in this country being used to run the cloud computing. So, so what are you going to do? I mean, so that's I think one of the interesting challenges going forward. The title of this National Academy report was, you know, Game Over, Next Level, which was, you know, is the golden age of integrated circuits over, or is there some next level that can take it going forward? And sort of by conclusion, I'll try and talk about this for a minute, is, well, a couple things here. One is we need some successor to the current CMOS devices and circuits. And we also need computer architectures that go beyond the fundamental architectures of von Neumann, Turing, and the German guy, which I just forgot. Yes, none of his machines made it through World War II. So, you know, so I think, you know, the right way to look at this is every technological device, every technology is really an S-curve. And Moore's law, at the front of the S-curve looks a whole lot, or is a whole lot like exponential growth. And Moore's law is the first part of this S-curve. And we're now at the inflection. So, you know, Intel will say Moore's law is going to continue, and there is going to be progress made. But they're now fighting the upper part of this curve on standard CMOS circuits. And so, I mean, I think you've got to think about how you move forward. One of the, as I was CTO at ADI, and we had a lot of experts in circuit design, I said, look, you've got to, as you look at these electronics products, there's a whole stack of technologies here, and you can't focus on one at the exclusion of the others. And you need to look at innovations, you know, all the way from materials and low-end device structures, through circuits, component architectures, and really right up through embedded software. One of my other jobs, CTO, is I've been on the CTO council of the SRC, the SI, the Semiconductor Industry Association, and we do a survey, and you know, it surprises some people that the semiconductor companies in the U.S. employ more software engineers than hardware designers, because you know, much of the complexity, a lot of the complexity has to be handled by the software, and a lot of that software is becoming embedded software going forward. So let me just talk a little bit about, at this point, some things I've been involved with, both at ADI and the company, but also some university research I'm working with, to say, here are some examples of the kinds of things that say, well, what would a different architecture look like? What would a different device look like? So I'm on this one very interesting project at MIT, which is saying, you know, Moore's law, all this progress with integrated circuits, it's all been innovations on a, now it's on automatic going forward. All of the innovations on this two-dimensional surface. So you need to somehow move to the third dimension. So this picture is sort of the goal for this. I'll go to this. So see if I get to the stop. See if I can get to the stop here. This is where I want it to be here. So what we're looking at is building what are called carbon nanotube transistors. And they really are just an ordinary CMOS transistor structure, except the channel is built with carbon nanotubes. And the great thing about carbon nanotubes is, as my material science friends tell me, it's a two-dimensional material. It's like graphene. And a two-dimensional material, by the way the bonds work in the carbon, there's these things called pi bonds. It's higher electron mobility, which would help. And there's a couple of other things you can go after as well. So number one, you can get a lower EDP, energy delay product. And the second one, if I get this to stop here, is the great thing is when you make an ordinary CMOS transistor, you build the channel by building the diffusion layer into the silicon, which is a 1,000-degree centigrade process. Depositing carbon nanotubes onto the wafer is a low-temperature process. You're just taking these carbon nanotubes in solution, putting that solution on the wafer, and then finding the right way to evaporate the fluid, leaving a layer of carbon nanotubes that can provide the circuit. So now I'll stop trying to hang on to this and see if I can move this forward. Okay. So that's the basic core idea, which is both being able to move to 3 dimensions and being able to have a higher performance CMOS device by working with carbon nanotubes. And then the other one, this might not stop either, we'll see what happens. The other one is a large part of the performance limitation is moving the data from memory to where it's going to get computed, so the processing element. People call it the memory wall or the delay between memory and processors. And one view is try and merge the processing into the memory. And there's some work of that going on here at Michigan, which is I think, a very innovative and high potential idea. The other thing you can do, if you can build 3D integrated circuits, is you can put the memory directly above the processing elements and use interlayer vias to tie them together. And if this one will not jump forward too fast, maybe I'll get this. So, today I've been a big proponent of interlayer vias where you'd have your processing down here on a separate silicon chip. It didn't stick. On a separate chip, you'd have the memory, thin the wafer, and then build vias that go down below it, and then connect them. It really runs forward here, doesn't it? So let's go back. And then, but in 3D, you're just using the regular interlayer vias that go along with. So you put 3 layers of metal down, and then planarize it. Put your carbon nanotubes down, and then put more layers of metal on top of that. You can keep going, and it gets, as you go up higher and higher, it gets harder and harder to keep the wafer planar. But we've gone 4 or 5 layers in some experimental areas. Now this last one, which I think, I'll just go to this one here. I don't think this will skip forward. So as we were doing that, and we've actually begun trying to look how to move some of this to, this really won't stop, move it into a product. I said, we need to have some application that actually drove this. And so we began working with Mass General Hospital and our healthcare business unit to say we can make great sensors out of this, where we'll put the sensor on the top layer and get the memory and the storage below it. So that's what we've done. Hopefully this will stop, maybe it won't. So we've begun, here's an example of a carbon nanotube array of sensors. This is the first experimental one we're using over at the hospital right now. It's just one layer. We're now in the process of making that a layer above the silicon that's going to process it. And by getting our healthcare business unit tied into this first application of a genuine 3D chip, we're hoping to sort of generate the level of commercial interest that lets us let's take forward on this. So that was my quick review of carbon nanotubes because it forced me forward through it. The other area that I'm working on now, in addition to these carbon nanotubes, is the area of security. And this got started for me one of my last years as CTO. And the job of a CTO is to go with our CEO to major customers and talk to them about our next generation of products. And I began talking about these 3 waves, and particularly the industrial folks were very interested to more fully automate their factories, both petrochemical as well as assembly factories. But we would get 20 minutes into that discussion, and they would say, wait, how are these thousands of sensors in our factory not going to be this attack surface that is going to make our whole automated structure a victim of various viruses and other attacks? And at that time, in our company, we really had not had a focus on security at all. We'd assumed that was going to be handled by computer sciences and software engineers. And as we did it, we began to more fully understand in any of these systems, you need a root of trust and a set of tools to be able to build truly secure systems. And so in the little bit of time I've got here, I was going to give you sort of my top level view of security that I've been spending time in the company trying to convince a semiconductor company they need to get serious about security. And the way I told them to look at it is there's a couple of levels in security. And at a core level, there's what most people know about. There's encryption. There's both symmetric encryption for being able to encrypt messages going across the networks, as well as what's called the public key encryption, where you've got public-private key pairs, so you can more effectively do authentication. And on this layer, the mathematics behind symmetric and public key or asymmetric encryption is well understood. It's been through several generations. The fact that these algorithms are open source, I mean, they were not open source 30 years ago. When I started in this area, the NSA and others thought that they could keep these encryption schemes more secure by keeping the actual algorithm itself secure. And then they found out that the best way to really vet an encryption algorithm is to make it open source and challenge the world to attack it and see how secure you can make it. And that's happened. And many mathematicians across the world right now spend their time analyzing both the current AES encryptions as well as both elliptic curve and RSA encryption, trying to understand how secure it really is, and coming up with small proofs on the side which show that they can attack a few bits, but still it stays sufficiently strong that there aren't enough years left in the life of the sun to be able to crack AES 256, our elliptic curve encryption, until quantum computers come along, and that's another story. But that's a few years away. Then the second level are a set of security protocols that use encryption to be able to authenticate these remote devices and these remote networks, and be able to authenticate that they're not counterfeits, they've not been compromised, and then you can use symmetric key encryption to communicate between them. And I would say likewise, these security protocols are also very secure. That's supposed to, this is light green. Okay, great. So you've got this base that's been well developed over the years. But then it gets a lot tougher when you go to implementing systems in hardware and software. My software friends at both of the companies I'm in like to argue with me about this, but every academic paper I've seen and every piece of sort of experimental work I've seen supports the fact that within any couple thousand lines of software code, and that code could be Verilog if it's going into hardware, or it can be in software, every couple thousand lines of code, there's a dozen or more areas of bugs or weaknesses that potentially adversaries can exploit. In the early days, they're obvious bugs and they're quickly exploited. We find out about those, we fix those. But there remain, still remain another dozen or so weaknesses in that code, and the adversaries with more work will discover those. And it's this attack, counterattack, attack, defense. This is going to go on for a long time, I mean, for those people that are thinking about, you know, what's a very employable expertise to have going forward, believe me, understanding how to build secure systems is not a problem that's going to be solved, I think, in any of your lifetimes, actually. It's like building a good defense. So there's a large problem there. So that's where we get some real problems. And then if you go to my final level, just in this very high level view, if you look at human behavior, many of the ways that systems get ultimately attacked is by what's called social engineering, where the adversary, via some mechanism, sends a phishing attack, which people think is real, respond to it, opens up a hole, and they move in. And it, you know, at one level, you're saying, well, given that humans aren't going to change, and there's always going to be these social engineering approaches, you know, aren't we just stuck? And I think the opportunity here is to use the tools that are very powerful, the encryption and various security protocols. Use those tools to understand how to build better hardware, software implementations, and actually how to avoid a lot of the social engineering attacks that have caused and continue to cause a lot of problems. And you know, this is you know, only one chart. This is an enormous area. I know there's work going on here in Michigan and other places. And as I say, this I think is going to be a long an area where there's quite a bit of work on going forward. So let's see. I'm getting close to the end here. So yeah, this is sort of my summary, which is, if you look at where we are right now, which is I think is the beginning of the third revolution, I got 2 minutes here. I would say, as I've been trying to understand sort of where this computing revolution goes ultimately, I ended up taking this open source course on the Industrial Revolution and watched how long that took to play out. And the Industrial Revolution actually took a couple hundred years to fully play out. And if you look at sort of what the stages of that were, I think it's pretty clear, although the world's moving faster now than it did during the prior century. We're only halfway through this information revolution. You know, there may well be a fourth wave after this third wave. But you know, Moore's Law gave us a wonderful run during the first 2 waves and provided a lot, and we found applications that drove them. There's going to be another 50 years of you know, phenomenal progress. You know, some of it looks pretty scary, but some of it looks quite promising. Hopefully, the people who are involved with it help makes it a promising, where this is used for good rather than not. But I think, you know, we're like halfway through it. And in the near term, at least the areas that I see from the technology point of view that really need is, you know, the next generation of circuits and devices beyond CMOS. You know, and you know, if you look back just a little bit, you know, people moved from bipolar to CMOS devices some number of years ago, and that's going to be happening again. And on computer architectures, I didn't have good charts on that here, but it's we're right now sort of reorganizing the way we do processor design at ADI with the realization that those chips that compute well, the neural networks and the AI algorithms, are really quite different from the standard, you know, fetch, decode, execute instructions of von Neumann machines. And how do you do that? And how do you do that with sparse networks so that you can efficiently move enough data out of memory and keep those execution units busy so that you actually get the performance that you need out of it is a big challenge. And just like people went through, I had the good fortune to go through like 20 or 30 years of continuing to optimize how you made a traditional von Neumann machine faster with speculative execution and parallel compute units and so forth. The same thing's going to happen with these alternative processors for AI and machine learning. And then I talked about the security a bit, which I think is going to be a critical capability going forward. And you know, beyond, people talked a little bit in comments earlier this morning about getting some collaboration between EECS and other areas of the university in liberal arts and policy and so forth, and understanding what are the applications that are going to actually drive the business that allow this third wave to actually move up another 3 orders of magnitude in the number of computings that are provided out there. So I raced through this without a lot of questions, but there are a lot of students in the audience here. And I really think that you have as much or more opportunity to find some really exciting challenges that will interest you going forward, as I found 50 years ago as I left here. So why don't I stop now and see if any of you have any comments or questions before I let you go?